Mr. Chairman, for your introduction. Today I'm going to talk to you about thermal and mechanical local effects in pseudoelastic nickel titanium alloy under fatigue loads. So actually this is part of a main project which the aim is to evaluate the fatigue resistance of the nickel titanium pseudoelastic alloy, with the aim also to investigate the local effect involved typically when you are dealing with fatigue. These actually are some work we have already published about the characterization of the material and about non-indentation performed on the surface of the material after failure in order to investigate how the stabilized marking site is involved in the fatigue resistant process. Today I just want to talk to you about the local effect involved during fatigue loads in nickel titanium shaped memory alloy from a mechanical point of view, with the help of the digital image correlation, and from a thermal point of view. So, the main approach of the work is based on a strain control fatigue test performed on the pseudoelastic material, and we used two fluid measurements technique to evaluate the strain evolution during the load history and to evaluate the thermal evolution during the load history. This is actually the material we use in the experimental campaign. It is a commercial near-rich pseudoelastic alloy, and as you can see from the monotonic stress response and the thermogram, we have a typical pseudoelastic response of the material. Those are the samples, dog bone shaped. We actually investigated 12 strain level, and we performed one repetition for each strain level for the accuracy of the results. And this is the experimental setup we have used. It's composed by a camera to catch the pictures for the image correlation, a thermal camera to evaluate the thermal evolution during the load history. For this experiment, we need to treat the surface of the samples. One surface was black painted in order to increase the emissivity of the sample and get accurate results in terms of thermal evolution. The other side was treated in order to get a random grayscale distribution for the digital image correlation. So how we perform the experiment they are based on a strain control fatigue test, and typically are performed in two different stages. First stage is the functional stabilization of the material. So we performed a strain control fatigue test, but with no fixed strain ratio, okay, in order to avoid, of course, compression phenomena during the unloading stage. When the material is stabilized, we continue the experimental test with a constant strain ratio, and we counted the number of cycles to failure. So typically when we are dealing with fatigue in smart material, it's really important to distinguish between functional fatigue and structural fatigue. Functional fatigue means investigate the ratcheting effect, so the residual strain, the evolution of the stress-strain response, and so on. When you are dealing with structural fatigue, it means investigate on the number of cycles to failure as a function of the stress or the strain you are applying. In this presentation, we just to discuss about both the aspects. So the functional behavior and the structural behavior, but not only from a global point of view, but mainly from a local point of view. So let's start with functional fatigue. Functional fatigue, you can study this aspect from a global point of view, just reading the stress-strain response of the material. So when you apply a load history, the material evolves. So there is a ratcheting effect, there is an evolution of the hysteresis, and you can read from here. But if you want to understand how the material is stretched, the strain evolution on the surface of the material, you can use a digital image correlation. So in this case, you can see a small movie. I hope it works. Okay. So this actually, in the linear elastic range, when you are in the stress plateau, there is a formation of something like slip bands, but those are not slip bands, but martensitic bands. So when you remove the load, of course, the martensitic bands tends to vanish, but at the first cycle they tend to vanish. But if you continue to work of course, you have a ratcheting effect, an accumulation of the residual strain. It means accumulation of a Martensite strain. So, if you want to study the evolution of the residual strain, you can easily read the stress strain response after 1 cycle, 10 cycles, 150 cycles, and so on. As you can see, there is a ratcheting effect, accumulation of strain, and typically it tends to stabilize after 150 to 200 cycles, as you can read also in literature. But if you want to understand how the martensite is kept inside the material, so you can easily use the digital image correlation. How? So you correlate the pictures recorded in stress-free conditions at 10 cycles, 150 cycles, and so on, and you have to compare with the stress-free picture recorded at the first cycle. So in this case, you can easily see what happens. After 10 cycles, there is a residual strain. This is residual martensite. After 150 cycles, the residual strain increases, but after 150, I will not expect a huge change of the material. And typically, this is what happens. So here you don't have a big change. Here you don't have a big change between 200 and 500 cycles. So this is just a main view of what happens when you want to study the stabilization of the material in terms of strain. Those are residual strain as a function of number of cycles for different maximum applied strain. You have a big gradient at the beginning, but after 200 cycles the behavior is almost steady state. And those are the stabilized stress strain response for different maximum applied strain. So you see the huge ratcheting effect at 8%, 7%, and so on. And this is what happens from a local point of view. Those are the stabilized strain, stabilized martensite for different maximum strain. Here you are working in the elastic regime, so no slip bands, no martensitic bands, sorry. Here you are working inside the stress plateau, so there is some residual martensite, and so on. So let's start studying what happens from a thermal point of view. So if you take a look at the movie, so typically when you increase the load, you have a very high increase of the temperature. When you remove the load, the temperature goes down. Why? Because typically the direct phase transformation from austenite to martensite is an endothermic transformation. When you go down with the load, the reverse transformation is exothermic transformation, so the temperature tends to go down. This is a famous phenomenon called in literature elastocaloric cooling effect. And typically, this can help the people to design a new refrigerator system. It's an ideal hypothesis, but you know, the nickel titanium is very expensive, so I don't know if this would be true. If you want, for example, to analyze the temperature evolution of this black box, and you want to monitor the maximum temperature inside this box and the minimum temperature, this is the typical evolution. So you can see at the first cycle, the temperature is very high because a huge amount of the material is involved in the phase transformation. After the stabilization, no more a huge amount of material is involved in the phase transformation, so you don't have a huge increase of the temperature. And the same approach you can use for the minimum temperature recorded on the box. You can see at the first cycles, the temperature tends to go down below the room temperature. So this is the elastocaloric cooling effect. This is just a comparison between the mechanical stress hysteresis and the thermal hysteresis. As you can see, if you work in the elastic regime, you don't have here martensitic bands, and the temperature doesn't go up very quickly. If you continue to apply the stress, you have here martensitic bands, the temperature go up very quickly, and so on. When you remove the load, of course, the martensitic bands tend to vanish, and the temperature tends to go down. If you compare, okay, so if you want to understand how the evolution of the thermal and mechanical hysteresis, you clearly see that when you continue to apply the load, both the mechanical and thermal hysteresis tends to get a narrow hysteresis. This is because no huge amount of material is involved in the phase transformation anymore. So let's talk about a little bit the structural fatigue. to conclude the presentation. Before discuss our results, I want just to show you some literature. This is a very famous work proposed by Figueredo and Fatiguel, where they show a very strange behavior in the pseudoelastic regime. There is a range where, if you increase the applied strain, it seems that the fatigue life tends to increase. This is very strange. In our previous paper, we just studied the fatigue resistance in the stress plateau. In this work we are presenting now, we are studying also the elastic regime of the arsenite and also the elastic regime of the martensite. So we went down with the maximum strain and we went up to the maximum strain. So this is what we got. If you report, I want just to discuss a little bit about how they are presenting the results. So here you have maximum applied strain as a function of the number of cycles to failure. They are not able to evaluate how the strain handled during the cycles, okay, the evolution of the strain, because they are fixing the strain and they just plot the maximum strain as a function of the log. So if we do the same approach with our results, we just clearly see here that there is a zeta-shaped effect like the Figueredo paper. And the very strange thing is that when you work alone from, when you work far away from the stress plateau, the material seems to show a behavior very similar to the most common metals. When you go inside the stress plateau, the material starts to show a very strange behavior. So you increase the applied strain, but there is no big change in terms of fatigue resistance. You can see here. And when you go up, and you start to go far away, again from the stress plateau, the material seems to show again a common behavior. Okay? So this is what we actually got, but this is maximum strain like Figueredo as a function of the number of cycles to failure. So I just remember you that we distinguish between functional fatigue and structural fatigue. So structural fatigue, it means that you have to delay what happens before the stabilization of the material and to evaluate the structural behavior, so the number of cycles to failure when you work in this range, so the strain amplitude. So if you study the strain amplitude as a function of the number of cycles to failure, so it seems that actually this trend, the zeta shape, seems to vanish. But of course, this could be a simple scale effect. Okay? Okay, but another aspect to consider is that the typical behavior of the smart material is different from the most common metals. When you apply a very high strain in a common metals, you have a very big slip plane. So if you study the global response in terms of a strain recorded with a big extensometer and you compare these results with a local response, maybe there is no big difference. But if you work with a smart material, of course, the martensitic bands that for us, they are the main parameter involved in the fatigue resistance. Maybe you have to understand well how to behave in this case, because I think we think that actually if you study the global response with a big extensometer and with a small extensometer, the difference will exist. So we are working on just to understand if it's really important to localize our attention to a local investigation instead of a global investigation. In fact, if you plot the results obtained with this virtual extensometer using the digital image correlation, the behavior clearly changes, especially in the stress plateau range. So those points tend to go up. Okay? So we are just trying to understand how to get a better interpretation of this kind of result. But just in conclusion, I want to tell you that typically when you work with this kind of material, we have to think in another way. It's really important to perform local investigation, and it's really important also to consider the thermal effect of the smart material that typically are involved, because nickel, titanium, and smart material are very, very temperature sensitive. Okay, thank you. Thank you.